Hello, Hornets. In this video, we're going to be taking a look at optimization. Now, be aware this is going to be a little bit of a longer video, so hang in there with me as we go through it. First of all, let me begin by saying optimization is simply a process of finding an extrema. So we're trying to find a relative maximum or relative minimum. Now, this could be an absolute maximum, it could be an absolute minimum, but it's depending upon what we need. If I'm looking for the least of something, that's an absolute minimum. If I'm looking for the most of something, I'm asking for an absolute maximum. If, however, I have on an interval find the maximum, now I could be looking for a relative extrema. Okay? So it all depends upon what we have. Now, in case you're not sure, when we're talking about finding an extrema, that means that we're looking for a derivative. Once we take a derivative explicitly, we are then going to be finding in that derivative using the first derivative test where our critical values are, and then the sign plus to minus, minus to plus. Now, therein lies the problem. Optimization almost always involves more than one variable. But we're trying to do explicit derivatives, explicit differentiation, as opposed to implicit differentiation, and that forces us to get rid of one or more variables. See, therein lies the issue. So what we're talking about in optimization is a formula that has more than one variable, and we need to have more formulas to convert all of the variables into one variable. Okay, so we're going to start taking a look at that. Be aware, all of these formulas that connect are called linking formulas. So here we have finding two positive numbers whose product is 185 and the sum is a maximum. So I'm looking for my sum of two numbers, x and y. Oh no, look at that. We have two variables. I need a linking equation. Now, amongst the information, they will always give you enough, or they will reference something that you will need. In this case, they are telling us that the product x times y is 185, and therefore I know that either x equals 185 divided by y, or y equals 185 divided by x. Now I can clearly see based upon this that regardless of which one I solve for, I'm going to get the same answer. So in this problem, I'm going to turn everything into terms of x. So I'm calling this the sum in terms of x is now x plus my y, 185 divided by x. I need my derivative. S prime of x is now 1 minus 185 over x squared. Now, if you didn't get the way I took my derivative, please be aware what I did was x plus 185, x to the minus 1, 1 minus 185, x to the minus second, and then I changed it back. Now, once I have my derivative, I need to get the common denominator so that I can find the zero. Notice x squared minus 185 over x squared, that's still s prime of x, and therefore when I factor this, x plus the square root of 185, x minus the square root of 185 divided by x squared is f prime of x. My critical values are the negative root 185 and the positive root 185. Now, because they asked me for the maximum positive number, I know, or the positive number that will yield the minimum. I get rid of the negative. My x must be the square root of 185. And when I put the 185 in to find it with the x right here, my y turns out to be the same, 185. And so I have the two positive values, and I would write that in a sentence. So please be aware, you would still write a sentence, and you have all your work here. So our linking equation is this one right here. It was given in the information, and whatever we are being asked to maximize or minimize is what we are taking the derivative of. Let's take a look at another example. Find two positive numbers whose product is 184 and the sum of the first number plus 3 times the second number is a minimum. Make sure you can see that clearly. All right, so we're looking for the sum is the first number plus 3 times the second, and the product is 147. I once again am going to go y equals 147 divided by x, so that my s in terms of x is going to end up being x plus 3 times 147 over x. Now, I've already taken the opportunity to multiply this together, so I already know that I'm looking at 441 divided by x. Not that I knew it ahead of time, just that I was able to do it. Taking my derivative, s prime of x must then be 1 minus 441 over x squared, and therefore my s prime of x is going to end up being x squared minus 441 divided by x squared. Factoring allows me to have x plus root 441 and x minus root 441 divided by x squared, and this just turns out to be x plus 21 and x minus 21 all over x squared. Our critical values are therefore positive 21 and negative 21, and we are looking for the positive number. Since we also know that our y value is going to be 147 divided by 21, our y, let's just put that in, 147 divided by 21 is equal to 7. So the two values are 21 and 7. Notice here is my linking equation right here. Here is the equation they have me minimizing. And those are my two values right down at the bottom. Let's take a look now at a more difficult word problem. A rectangular solid with a square base has a surface area of 337.5 square centimeters. Find the dimensions that will result in a solid with a maximum volume. So the first thing I want to recognize is that I have a box. You notice I'm going to draw a picture of my box. My box has a square top, and we're going to call it X and X. Then has a very long, non-square. I just connect it all together. Now you'll notice my volume then is X squared Y. And my surface area is 2x squareds for the top and the bottom, and 4 xy's. So you'll notice if I'm trying to find the dimensions that will yield a solid with the maximum volume, this is what I have to work with. And I know the surface area is 337.5, and I need to find the variable that works best. It's going to be y. See how there's only one y? So that's what I solve for. 337.5 minus 2x squared divided by 4x is y. Now I'm going to put it back in so that I have my volume. My volume is x squared, 337.5 minus 2x squared. And I'm dividing by my 4x. Make sure I get that in. Now you notice the x's are going to reduce here so that my volume in terms of x, and I can now distribute it, is 337.5 minus 2x cubed. Oop, don't forget your x, over 4. Or x, 337.5 minus 2x squared over 4. I think I like that second one better because I can now take that 1/4 and bring it out in front. I don't know. Let's go ahead and just keep it in so that I can do my derivative quickly. And when I take my derivative in terms of x, I get 1/4, and this is just 337.5 minus 6x squared. And now I can factor it, just like I did with the other word problem. I can also solve it. And I got lots of choices here. That should have been, yeah, no, we're doing good. So I'm going to just kind of factor it. Make sure I follow my plan. Don't get lost, Mr. Lamb. Root 337.5 plus root 6x and root 337.5 minus root 6x. Now, once again, I'm looking for the positive yielded value. The positive value is the square root of 6 divided by the square root of 337.5. Make sure I've got that right. Oh, I have that upside down. Excuse me. There you go. Isn't that a fun one? Try that again. Make sure we flip it right side up. So we're looking for x equal to approximately the square root of 337.5 divided by root 6. It's actually exact, Mr. Lamb, until you make it a decimal. And then when I do this, it turns out to come exactly 7.5. Now I can go back and I can find my y value. So it's going to be right here. My y will end up equaling 337.5 minus 2 times 7.5, the quantity squared, divided by 4. And y is also 7.5. So I now know that the dimensions are 7.5 centimeters by 7.5 centimeters by 7.5 centimeters. All righty. So, ladies and gentlemen, this gives you a good idea of the linking functions, of the use of optimization, and this is the first part. I will do a second video, part 2 of optimization, that will go over more information. I hope this helps. Thank you very much. Be safe and be well. We will see you soon.